All right, and hello everybody, and welcome. I'm glad you're here. I've been doing work on the hydraulic cylinder robot. Boston Dynamics switched their robot to battery powered, and people have been acting like if it's not batteries, it's nothing. But I'm not so sure of that. And I've been working on that, but I didn't want you to. I have also been working on the hand, and this is an update about the hand. Of course, I want you to know I'm glad you're here. Please watch and enjoy. I do have a YouTube channel. I invite you to subscribe. I think you'll like it. I have a website, and there's a page there about robots, and there's a page here about give the robot a hand, and that has what I'm talking about. Always want to remind everyone anything that's physically real might hurt somebody. So if you have something that you created that's physically real and you're managing it, you have to manage it in a way that's legally allowed and reasonable and safe. And if you can't manage it that way, then my advice is do not create it as a physically real item. And we've been through, I guess this is as generated by me, Dr. Gray, the Turing test for a robot hand. My hand that I've designed can do all this. My hand is 4.5 inches wide across the back of the hand. The index finger is 4.9 inches long. The hand itself at the metacarpal phalangeal joint is about 2 inches thick. So it's pretty good on that issue of size, and it will also be able to hold up 200 pounds. I haven't proven that, but I will. And the only thing I remind everyone is people are going to think it's completely impossible. I'm going to go over how are we going to connect up these tiny little pistons that are giving us the intrinsic muscles of the robot hand. And I suppose we should take a look at what is. I thought this was ribbons of taffy out at the beach. Of course, I've been wrong before. It's actually the Hawaiian lei flower garlands. So there you go. Not taffy. Okay, we want to go look at something real quick. All right, say thanks to Physiopedia. Thanks, Physiopedia. Physiopedia. These are the internal muscles of the hand, or the intrinsic muscles of the hand. You can see how big they are. They're not very big. And the maximum strength that you can create with these muscles for humans is about 9 pounds of force. And I just wanted you to see them. So the little hydraulic cylinders that we're using for our robot hand, they don't make any more force than 9 pounds either, but that's okay. That's all that humans do. And this is just one of the hands in KeyShot, and I wanted you to see all these little hydraulic cylinders that are inside that hand. It's at 38. We'll let it res up a little bit. And all of these cylinders are giving motions to the finger. Each of these cylinders is about 28 millimeters long. It's about 4 or 5 millimeters in diameter. The distance it travels is about 22 millimeters. And a number, everybody is like, how are you going to get that to work exactly? And this is what we're talking about. It's here. It has the cardantic joint so it can move, but how are we going to get hydraulic pressure fluid to it? And I like to make everything pretty in KeyShot, but this is an update. I'm just going to show you what's going on in SketchUp because it's quicker and easier. And I just wanted to put this in. This is really nothing more than a teaser. I just thought it was cool. I thought making the floor reflect like a mirror was pretty neat. I'm going to do a discussion of how to get the robot to turn. So I'm going to show how to walk on a straight line. I'm going to show how to get it to turn. And I'm going to show how to get it up if it fell over. But that's all in the hydraulic cylinder stuff. And right now we're doing the hands. And I'm just putting this in because I just thought it was cool. There's more of this later. And I wanted you to see this Valco Chem Inert. They make parts for high pressure liquid chromatography with this tiny tubing. And the ultra high pressure fittings is on, it's made with PEEK, P-E-E-K, and they have their fittings, and this will work for what we're doing. And this is some of the fittings, one-piece fittings. They also do it where they have a ferrule in there that you put on the end of the tubing, and it squeezes it together, and it allows you to use this tubing and it won't leak. So that's what this company is. And here's a flanged PEEK tubing with a flange on it, and I've done some of that. But if you were wondering where that came from, that's where it came from. Here's a website of dimensional drawings for these fittings. And here they have this polymer PEEK material with the ferrule already built into it. Anyway, that's where I got all this stuff from. So the first question was, how are we going to connect up to this hydraulic cylinder? This is all drawn to scale. And we built this part here that goes on the end of the hydraulic cylinder. And we have a flange on the PEEK tubing. This PEEK tubing is 1.5 millimeters in diameter. It can take 3,800 pounds per square inch, and the internal dimension is 0.7 millimeters. We need 0.6 millimeters, so that's going to work. And I made this little nut, and I took this part and drilled a hole in it to connect it, and then you put a plug in here and weld it shut, and that way it doesn't leak. And so you can take your tubing here and screw in this little nut that pushes this PEEK tubing against the seal, and this then screws onto the hydraulic cylinder. And I put some gaskets in here to seal it, and I also put a packing nut gasket here. This nut screws down onto that and seals this against the shaft of the piston shaft, the piston rod. And this material is the iGlide material. It's fiber infused, lubrication infused polymer material that's used for gaskets, and it's used for packing. So this is a use for it. I don't know if they've got one this small, but there it is. And this PEEK tubing will come in and hook up. The long axis of the PEEK tubing will be parallel to the long axis of the hydraulic cylinder. And there's one more fitting that has to go down here. And I think that the PEEK tubing should come in this way, because this is what moves around. But this one, I think the PEEK tubing just comes in at a right angle. I haven't created that yet, but that's not nearly as hard as this, because this has to have the packing in there, and it has to screw on the end of the hydraulic cylinder, and it has to let you put the piston rod in there. You don't have to do anything with the connection down here. It's pretty simple. And so the next question is, how are we going to connect up this tubing to a valve? And here's the valve, and the valve is basically a 12 by 12, I think it's about 18 millimeter long block of stainless steel that has holes drilled in it by the electric discharge machining system. And the electric discharge machining people, if you go to their website, they're like, look, whatever you want, we can make. Just don't worry about it. And it's the same concept of drilling the tubing lines in and then sealing up the place where we drilled it with a plug that's welded. And so this allows the valve to be put in there. You'll notice that the stem of the valve is sitting inside of a press-fitted iGlide polymer bushing. And it has 4 connections. These are the ferrules. Here are the little ferrules. So the tubing goes through here. The ferrules go in there, and this gets pushed down on it by these bolts. And these bolts are going to pull down this, plus the ferrules, plus the tubing, plus the valve, plus a packing nut on this side, plus the DC motor gear drive. And I found this gear drive is like 12 by 15, and the whole thing is maybe 2 inches long. And so those bolts will pull all of this together, and this little electric motor will control how the fluid is distributed. And these tubing diameters are 6 millimeters, which is what we want. But you can see I made it, I took the opacity and lowered it so you can see, but this one here is red, so it brings pressurized fluid. It brings it to here and here. And this one is return, and it puts suction on here and here. So pressure and suction are here. And then these two, in one position of the valve, this one has pressure and that one has suction. And in the other position of the valve, this one has pressure and that one has suction. And I've already gone over this with another video. So that's how we're going to get the fluid to go to the little hydraulic cylinders of the hand. And the other thing I wanted to show you is this. Okay, so you can see we have this I-glide polymer bushing, and it has an asymmetrical shape so that when this is pushed into this block of metal, it won't turn. And the valve stem is symmetrical, so it will turn. And let's go over here and see something else, which is taking this I-glide material with the through channels in it and not doing that. And now we have the I-glide, it's still asymmetrical, and we can put tubing channels in it. We can make a metal device that has this asymmetrical channel in it and a cap, and we can make, if we wanted to, a metal item of this structure. And you might be saying, why is that? But this is the piston head and piston rod that slides inside of this polymer insert. So this is what I've drawn. Here is the polymer insert, and the polymer insert is inserted into this blue metal tubing. This is the hydraulic cylinder. And you're like, why are you doing all that? Well, the drawings that I do have no inherent scale to them. So this could be 40 millimeters or it could be 4 millimeters. And creating this hydraulic cylinder, if you don't have to have it absolutely perfect, is a lot easier. And the bushing material is forgiving. So all that happens is this diameter is a little larger than the hole in the bushing material, and so this bushing material squeezes on it and it won't leak. And you might say, what is this? And it's actually a spring, because I haven't finished it. SketchUp lets me draw a spring, but this is actually a copper wire, and it's the secret holy grail of how all of this works, because we finally have a sensory system inside the hydraulic cylinder. Because when this piston rod and piston move, okay, this is an inductor, and the amount of inductance that it has will change as this moves, which means you can have a lookup table where wherever the hydraulic cylinder piston rod has been placed by the valve, the central processing unit will know it by measuring the inductance. It's my hope that this works at 2 millimeters or 4 millimeters diameter, but I'm really hoping that it works at 40 and 100 millimeters diameter, because that can be used on the hydraulic cylinders of the piston robot. And Texas Instruments makes an test setup device that measures inductance for you. And so I might get some polyethylene tubing and some copper wire, and I'll take a bolt and push it in and out of here and see if I can measure where this is, if the market will let me. Anyway, she's waving her hands in the air and pointing at me, which is the signal of stop talking. So It's just an update.